Welcome to this lecture on beer fermentation and pandemic charts. First, a disclaimer: I am not a medical doctor and I am not an epidemiologist. I'm a scientist and I'm a home brewer, and I'm going to try and make sense of some of these charts that we see for this present pandemic, along with some references to fermentation. So you have seen some of these charts in the news that we continue to encounter with our updates on the current pandemic with COVID-19. And you've also seen graphics of this sort about flattening the curve. What do these graphics actually mean, and how can we understand these graphics? So the first thing to do is to quickly look at a very simple plot here of cumulative growth versus time. A good example I can give you for cumulative growth here is, let's say you are going to look at the consumption of your beverage or a drink. In this case, let's say we are going to look at consumption of beer. So let's say you are one of these people who drink one beer every day, like the lady that we saw in the news recently, the 93-year-old woman from Pennsylvania who drank a beer every night and ran out of beer. So we're going to count the number of beers we drink in the course of a number of days. So on day one, we're going to drink one beer, the next day another one. So after 2 days, we have drank a total of 2 beers, 3 beers after 3 days, 4 beers. Our total number of beers consumed is 4. This is an example of a linear increase of cumulative growth, and this line has a constant slope. And the growth here is by addition. We are adding one beer every day to the total number of beers consumed. Now let's look at another example of consumption here, where we are going to increase our consumption by a factor of 2 here. So we're going to start by drinking one beer on day 1, 2 beers on the second day, 4 beers on the third day, 8 beers the following day, and so on and so forth. This would be a great way for you to make a trip to the hospital without getting COVID-19. Probably by day 4 or day 5, you're going to end up in the hospital. So now let's look at what does this mean for our cumulative growth. So previously, we were just looking at our consumption. That this is the amount of consumption is increasing by a factor of 2. We are now going to look at cumulative growth. So after 2 days, we have actually now consumed a total of 3 beers. And after 3 days, we have consumed a total of 7 beers, and so on and so forth. And the numbers are going to increase dramatically here because our consumption rate is going up by a factor of 2. This is what is known as exponential increase. So in this case, our slope of our line is getting steeper and steeper with time because our growth rate is being defined by a multiplication factor. And lastly, we are now going to look at slowing down our consumption here. So day 1, 1 beer. Next day, let's say we only drink half a beer. And the day after that, a third of a beer. And the day after that, a quarter of a beer, and so on and so forth. So in this case, we are adding a fraction of a beer to our increase. And even though the total number of beers consumed is increasing over time, the slope is getting less steep. This is called a logarithmic increase. And in this case, our growth rate is decreasing over time. So here we can see these comparisons of these 3 different growth rates and how they influence our cumulative growth. So exponential growth, linear growth, and a logarithmic increase here. The next thing we're going to do is we're going to look at scales. So we're going to first compare arithmetic scales with logarithmic scales. So previously on all these plots that I just showed you, we had essentially an arithmetic scale. There were no numbers, but imagine that the numbers are increasing in the linear fashion. And what that means is that the spacing of the numbers is even. Every single space here is representing the same amount of increase. For a logarithmic scale, this space here between 100 and 1,000 is the same as the space between 1,000 and 10,000 on this axis. So that's going to actually be a very dramatic change in the scale. So what does this mean for some of our plots? So on our exponential increase, this is what our plot was looking like with the arithmetic scale. If you were to plot an exponential cumulative growth on a logarithmic chart, it turns out that it actually becomes a straight line. If you were to try and plot a linear increase from an arithmetic scale onto a logarithmic scale, this is what the linear scale is going to turn into. So to recap quickly here, with our logarithmic scales, a straight line on a logarithmic scale is going to represent exponential increase, and a downward curving line is representing a linear increase. So let's look at some actual examples here for the COVID-19 pandemic. So this is the data from today, from April 30th. And I will just briefly point out that this is an excellent source of data, the website ourworldindata.org, where you can modify these plots, change the scales, pick what countries you want to look at, etc., etc. So here I have chosen to plot the cases, total number of confirmed cases for the US, Europe, UK, and Germany. And in this case, I've chosen them on a linear scale on the y-axis. And I'm going to turn this into a log scale, and you're going to see here very soon that this changes the plot dramatically. You will immediately notice that all the lines are looking as curves in this case, and they look very, very similar in their shapes. They look to be following essentially very similar paths, just at different levels on this chart. So what does this mean for plots like this, where we talk about flattening the curves? For that, we need to look at fermentation. So this is my beer fermenter here after 24 hours of fermentation, after adding yeast to my fermenter. And you will notice here that the yeast has just begun to ferment, and I have a little bit of foam starting to form on my fermenter. In a matter of few hours, it's gone from this to a pretty big head of foam here, lots of bubbling, and in short order, in less than the next day, in this case actually, it blew over my top of my airlock and had a big mess on my hands. So yeast growth has been studied by scientists and biologists, and we can look at this with time, again, just like with our pandemic graphs before, and we're going to plot cell density, in this case, on a log scale on the y-axis, even though I'm not putting any units. We're just going to have a representative plot. This is what the representative plot looks like. Initially, I have a lag phase where the yeast are just getting adjusted to this new environment. They haven't actually started multiplying yet in great deal. They have not started digesting the sugars yet, but very shortly they are going to be doing those two things, and that's going to produce an exponential growth in the amount of yeast cells in my fermenter. And then it's going to stabilize for the next few weeks, after which time the yeast would have consumed all the food and they will start dying. And after that fermentation is over, I will have a nice glass of beer here to enjoy. So this is what this looks like for the rate of growth. So this is actually the key here, is to look at the rate of growth. So initially in my fermenter, I have exponential growth, followed by linear growth perhaps, followed by a long phase of relatively stable growth, and then a slow decrease of yeast cells over time. So now we can actually start looking at these graphics. So on this particular plot, I want to point out this y-axis here that says number of cases. And many of the graphs that you would have seen, these graphics that you would have seen in the news, will label this axis as number of cases. And I would actually point out that this is actually not correct. We need to change that label to the daily number of cases and not number of cases. In other words, that y-axis is not representing cumulative growth. It's telling you the daily number of cases. So that's what we need to actually look at. So if you were to actually start looking at the daily confirmed cases across the world, and in this case, this is on a linear axis, this is what it looks like. Again, I've chosen Europe, the US, UK, and Germany here. And you can see that initially the number of cases was increasing, exponentially, then followed by a more or less linear increase, and now that growth has actually stabilized, and in many cases is actually starting to go down. If I switch this to the logarithmic scale, that actually becomes really good to look at and to compare. Again, in this case, a straight line on a log scale is telling me exponential increase. So in this case, initially, the early part of March, I was having exponential increase in the number of cases, followed by a linear growth. And right now, it seems to have stabilized for the most part in most of these cases. Again, note that these are still pretty large numbers, several thousands or tens of thousands of cases, new cases showing up every day. So even though we are stabilizing, this is what it actually means to be flattening the curve. So in other words, our social distancing measures that have been put in place for the last several weeks are working. We have slowed down the rate. The curve has actually become flat. This is what this flattening the curve term refers to. So finally, just want to look at this first graph that I showed you before. These are the graphs that again you will see. And in this case, you will notice that there are straight lines that have been put on these graphs that are representing the rates of exponential increase. In this case, the doubling of cases, so a factor of 2. So this line would represent a doubling every 3 days. That's representing every 2 days. And the further down this direction you turn your plot or turn your line, the rate of doubling has slowed down. So hope you enjoyed this little tiny talk on the comparison of beer fermentation and these pandemic charts. Thank you.